Okay, so let's look at exercise 1.4. We have to show whether this language is or isn't context-free. And good intuition for this one is, if you imagine a PDA trying to recognize this language, it pushes all the A's on the stack, and then pops off the A's as it's reading the B's to count that they're the same. But then when it gets to the C's, it's got no more information left to check if the C's match the A's and B's. So intuitively, this is not going to be context-free. And we're going to prove it using the same trick we did before, the pumping lemma. Okay, so by the pumping lemma, there exists some natural number such that for all strings in the language sufficiently long, the pumping lemma applies. Okay, so we're going to choose some string at least that long in the language. And I guess the obvious choice is to choose n many A's, n many B's, n many C's. The length of this thing is 3n, which is clearly at least as large as n. So this string is definitely going to be in the language. Okay, so there exists some decomposition, and now it's going to get a little tricky because we're not sure where this middle region could be. If I sort of write a bunch of A's and then a bunch of B's and a bunch of C's, the middle region could be somewhere here overlapping the A's and B's, or it could be somewhere here overlapping the B's and C's, but it can't have all three characters, because if it had all three characters, it'd have to be at least this long. It'd have to be at least as long as n plus 2 many characters, which violates the first condition of the pumping lemma. So we only have two cases to consider, A's and B's or B's and C's. So we'll do cases. So what we decompose, z equals u, v, w, x, y. So the first case is v, w, x is some string of zeros and some string of ones, possibly empty, as in it could like be entire, I beg your pardon, sorry, A's and B's, sorry. A to the I, B to the J. So it could be the case that it's entirely just A's and no B's, or entirely just B's and no A's, but there can't be any C's slipped in just for the moment. So we're looking at like any decomposition somewhere in this region. Okay, so now what? Well, we can write down what U is. U is going to be however many A's are left over. How many A's are going to be left over? N take I. Because there were n A's, and the middle part's gobbled up I of them. And then what's Y? Well, Y is going to be however many B's are left over, and then all of the C's. Okay, so what does the third condition give us? It gives us for all m greater than 0, if you pump up the V's and X's, so U, V, W, X, Y, put m's here, is still in the language. So I'm going to choose m to be 0. So U, W, Y is in the language. So 0 to the, sorry, I keep thinking zeros. A to the n take I, that's U. And then W, well, we don't really know what W is because we don't really know what V and X is. So writing out an explicit decomposition might be tricky. So what else can we do? Well, we can reason, because V, W, and X, well, V, X is non-empty, right? Rule 2 tells us that. Which means when we deleted the V and the X, we lost at least one A, or at least one B, or possibly more than that, right? But this string here is going to have the same number of C's in it because all of the C's are inside the string Y, and Y didn't get modified. So this string here is going to have exactly n many C's, but it's going to have either fewer than n many A's or fewer than n many B's. So in either case, that's going to give us a contradiction. Okay? So the proof would be to sort of write that out in full, because if you tried to do it in nitty-gritty details in terms of decomposing what V and X would be, you'd be here all day, right? So what's the other case it could be? Well, I guess the decomposition could be somewhere to the right of this barrier. So if it's somewhere over here, that means it's going to be B's and C's. So case number 2, VWX is B to the I, C to the J. So what's U going to be? U is going to be all of the A's, and then however many B's are left over. And then Y is going to be however many C's are left over. And then you do exactly the same argument as before, right? You choose M to be 0. So therefore U, W, Y is in the language. And then U contains all of the A's. This has got n many A's in it. and this string's what's left over, well, if we deleted the v and the x, we had to have deleted at least one a or at least one b. So this is going to have less than n b's or less than n c's. And in either case, this is going to unbalance the number of b's and c's relative to the number of a's. So it's not going to be in this language. So again, we get a contradiction. So in either case, we get a contradiction. Therefore, we made a bad assumption, so this language here cannot possibly be context-free.